Complex integration. Integral of a function with respect to the given curve gamma over an interval closed AB. Let gamma be a function from closed interval AB to C, be bounded variation, and suppose that f is a function from AB to C is continuous. Then there is a complex number I such that for every epsilon greater than 0, there is a delta greater than 0 such that when P is a partition of the interval closed AB with the norm of P is maximum of that small partition intervals length, that is maximum of tk minus 1, where k is varying from 1 to m. If maximum of this value is less than delta, then modulus of I minus sigma k is from 1 to m f of tk into gamma of tk minus gamma of tk minus 1. If this is less than epsilon, for whatever choice of the points tau k and tk minus 1 less than or equal to tau k less than or equal to tk. And this number I is called integral of our function with respect to gamma over the interval AB. And it is designed by I is equal to integral a to b f of gamma, f of t into d of gamma t, d gamma of t. I is integral a to b f of t into d gamma of t. And let gamma is a function from AB to C, be a bounded variation, and let f is a function from AB to C is continuous. And if there is a partition of the interval AB, then integral a to b f of d gamma is equal to sigma k is from 1 to n integral of tk minus 1 tk up to tk f of d gamma. Integral of summation of the integral of f of d gamma. If this gamma is piecewise smooth curve and f is a function, continuous function, then the integral f of d gamma is equal to integral a to b f of t into gamma dash of t dt. If gamma is a function from AB to C, is a rectifiable path, and f is a function defined and continuous on the trace of gamma, the integral of f along gamma is integral a to b f of gamma of t into gamma dash of t dt. The line integral is also denoted by integral over gamma f of t dt. That is, then the line integral is defined as integral over gamma f is integral over f of dz into f of z into dz. Integral of f is integral of f of z dz. If we have defined gamma is a function from our closed 0 to through a circle, we are defining this 0 to 2 pi to c by gamma of t is equal to e raised to it. Then define f of z is equal to 1 by z for z not equal to 0. Now gamma is differentiable, and we have integral of 1 by z dz is equal to integral over 0 to 2 pi. Substitute the value of z is equal to e raised to it. So for e raised to minus it into dz value. That is I e raised to it dt. So now gamma is differentiable. So by the theorem, we have integral of 1 by z dz is equal to, when z is equal to e raised to it, its value is 0 to 2 pi. f of t f of gamma into gamma dash of t dt. That will give you 2 pi I. And there is a theorem that let G be an open set in C and gamma is a rectifiable path in G with initial and endpoints alpha and beta respectively. If f is a continuous function with primitive f, then we have integral over gamma f of t dt is equal to capital F of beta minus at the endpoints, limit at the endpoints, that is f of beta minus f of gamma. That length of the interval will give you the integral of that value. And a curve gamma is said to be closed if gamma of A is equal to gamma of B. Let f is analytic in the disk B of AR and suppose that gamma is a closed rectifiable curve in B of AR, then integral over gamma f is equal to 0. So next we have a definition of what is a zero of an analytic function. An element A belongs to C is a zero of P of Z if and only if Z minus A is a factor of P of Z in C of Z. If P is a polynomial with a 0 A of multiplicity m, then P of Z is equal to Z minus A raised to m into T of Z, where T of Z is a polynomial such that T of A not equal to 0. If f is given as a function from G to C is analytic and A belongs to G satisfies f of A equal to 0, then A is a 0 of multiplicity m greater than or equal to 1. If there is an analytic function G such that f of Z is equal to Z minus A raised to m into G of Z. Where G of A value is not equal to 0, f of Z is equal to Z minus A raised to m into G of Z, then and G of A is not equal to 0, then we can say that this A is a 0 of multiplicity m greater than or equal to 1. A 0 of an analytic function f of Z is a value of Z for which f of Z is equal to 0. If Z0 is 0, then f of Z0 is also 0. If f of Z is equal to sin Z, then f of Z is an entire function and f of 0 is sin 0. If f dash of Z is equal to cos Z, then f dash of Z is equal to cos 0 is 1. So f has a 0 of order 1, and similarly so we can say that f has a 0 of order 1 at Z is equal to 0. If f of Z is equal to Z raised to 4 plus iz, then being a polynomial, f of Z is an entire function. So we have f of 0 is 0 and f dash of Z is 4z cube plus I, f dash of 0 is I, which is not, f dash of 0 is not equal to 0. So Z is a 0 of the this given function with order 1. And look at the other examples also. If f of Z is equal to Z cube plus 2iz square minus Z, then we can find that Z is equal to minus 1 is a 0 of order 2. A function f that is analytic at z0 has a 0 of order m at z0 if and only if there is a function g such that at which analytic and which is analytic and non-zero at z0. A function f is analytic at z0, has a 0 of order m if and only if there is a function g such that f of z is equal to z minus z0 into g of z. Let f of z is equal to, for example, z into e raised to z minus 1. Then f of z is an entire function and f of 0 is 0. F dash of 0 a function f that is analytic at z0 has a 0 of order m at z0 if f of z is equal to z minus z0 raised to m into g of z, where g of z is not equal to 0 and it is analytic also. Example, let f of z is equal to z into e raised to z minus 1. Then f of z is an entire function and you can see that f of 0 is 0 and f dash is 0 and so the derivative all becomes 0. So such kind of function is this. Therefore, we can say that f double dash of z is not equal to 0 when z is equal to 0. So, at z is equal to 0 is a 0 of order 2. Z equal to 0 is a 0 of order 2. An entire function is a function which is analytic in the entire complex plane. An entire function, these are also called the integral functions. If f is an entire function, then f has a power series expansion of the form f of z is sigma n is from 0 to infinity an into z raised to n. So with infinite radius of convergence. And look at this example, f of z is e raised to z. Then the series, it has a power series representation of the form sigma z raised to n by n factorial with infinite radius of convergence. We have an important theorem, Leoville's theorem. If f is bounded entire function, then f is reduced to a constant value. If f is a bounded entire function, that will become, then f is become a constant value. Suppose modulus of the absolute value of f of z is less than or equal to m for all points in C. Then we will show that we can, when we take the derivative, it will become, if it is a constant values, then derivative becomes 0 for all z in C. So we have to show that f dash of z is equal to 0. Since f is analytic in any disk B of zr, we have modulus of f dash of r is equal to, is less than or equal to capital M by r. So r has, when we choose r as arbitrary, it follows that f dash of z is equal to 0 for each z in omega. We have an important theorem, Leoville's theorem. If f is bounded entire function, then f is reduced to a constant value. Suppose that modulus of absolute value of f of z less than or equal to m for all z in C. We have to show that f dash of z is equal to 0 for all z in C. To do this, we use Cauchy's estimate. Since f is analytic in any disk B of zr, we have modulus of f dash is less than or equal to m by r. As r we choose arbitrary, it follows that f dash of z is equal to 0 for each z in C. So f dash is equal to 0, therefore our f will become a constant value. Next is also another important theorem, fundamental theorem of algebra. If p of z is a non-constant polynomial, then there is a complex number a with p of a equal to 0. Fundamental theorem of algebra says that if p of z is a non-constant polynomial, then there is a complex number a with p of a is 0. We are doing this proof by a contradictory method. We suppose that the non-constant polynomial p of z has no zeros in C. That is, p of z is not equal to 0 for all z in C. So if we write f of z is equal to 1 by p of z, then f is an entire function, p is not a constant value. So we can see that limit of z tends to infinity, p of z is goes to infinity, and limit z tends to infinity of f of z, that is going to 0. In particular, there is a number r greater than 0 such that modulus of f of z is less than 1 for mod z greater than r, but f is continuous on this interval b of 0r complement. So there is a constant m such that modulus of f of z is less than or equal to m for mod z less than or equal to r. So here f is bounded, and therefore it must be a constant that reduced to a constant value. Hence the non-constant polynomial p of z has a 0 in C. That is our fundamental theorem in this complex analysis. That is, if p is a constant, then that non-constant polynomial has a 0 in C. Next we have a Maxima modulus theorem. If G is a region and f is a function from G to C is an analytic function such that there is a point A belongs to G with the modulus of f of a greater than or equal to modulus of f of z for all z belongs to G, then Maximum modulus theorem. If G is a region and f is a function from G to C is an analytic function, then there is a point A belongs to G with modulus of f of a is greater than or equal to modulus of f of z. For all z belongs to G, then f is a constant. That is, maximum modulus theorem states that in complex analysis, if the given function is a holomorphic function, then the modulus cannot exhibit a strict local maximum that is properly within the domain of f. And we have index of a closed curve. If integral over c z minus a raised to n dz is equal to 2 pi I if n is equal to minus 1 and its value is 0 if n not equal to minus 1, where C is the circle mod z minus a is equal to r oriented in the anti-clockwise direction. Consider this example. Show that integral over gamma z minus a raised to minus 1 dz is equal to 2 pi I into n, where gamma is a curve given by the parameterization gamma of t is equal to a plus r e raised to 2 pi I n t with 0 less than or equal to t less than or equal to 1. So z is equal to gamma of t, that is a plus r e raised to 2 pi I n t. And we have dz is equal to, if z is equal to e raised to 2 2 pi I n t. So we have dz is r into 2 pi I n e raised to 2 pi I n t dt, and we have z minus a is r e raised to 2 pi I n t. So substitute those two values, all those values of z minus a and d of z. Then we have dz by z minus a will give you integral 0 to 1 r into 2 pi I n e raised to 2 pi I n t divided by r e raised to 2 pi I n t. Those two will get cancelled and you will get the answer as 2 pi I n into 1. That is 2 pi I n. If gamma is a function from closed 0, 1 to C, is a closed rectifiable curve in C, and a does not belongs to trace of gamma, then the integer 1 by 2 pi I integral over gamma dz by z minus a is called the index of gamma with respect to the point A, or it is called the winding number of gamma around the point A. That is, n gamma A is the winding number around A, which is equal to 1 by 2 pi I integral over gamma dz by z minus a. It is an important theorem we are applying in problems. That is, the winding number n gamma A is 1 by 2 pi I integral over gamma dz by z minus a. And n minus gamma of A, which is equal to 1 by 2 pi I integral over minus gamma dz by z minus a, that will have minus 1 by 2 pi I integral over gamma dz by z minus a. So n minus gamma of A will give you minus of n gamma of A. We have an important theorem and formula, Cauchy's integral theorem, and Cauchy's theorem and Cauchy-Goussat theorem and Cauchy's integral formula. Let gamma be a rectifiable curve, and suppose phi is a function defined and continuous on gamma, set gamma, for each m greater than or equal to 1. Let fm of z is equal to integral over gamma psi of omega by omega minus z raised to m. For z does not belongs to gamma, then each fm is analytic on c minus gamma, and f dash of fm dash of z is equal to m into fm plus 1 of z. Cauchy's integral formula. Let G be an open subset of the plane and f is a function from G to C, be an analytic function if gamma is a closed rectifiable curve in G such that n gamma omega is equal to 0 for all omega belongs to C minus G, then for A belongs to C minus G, G minus gamma, for A belongs to G minus gamma, n gamma A into f of A is equal to 1 by 2 pi I integral over gamma f of z by z minus a dz. That is, if gamma is a closed rectifiable curve such that n of gamma omega is 0, then for all A belongs to G minus gamma, our n gamma A into f of A is 1 by 2 pi I integral over gamma f of z by z minus a dz. If it is in powers, if fk of A into n gamma A is equal to k factorial by 2 pi I into integral over gamma f of z by z minus a raised to k plus 1 dz. If it is fk of A into n gamma A, then we have it is 1 by z minus a raised to k plus 1 dz. Morera's theorem. Let G be a region and f is a function from G to C be a continuous function such that integral over tau f is equal to 0 for every closed triangular path toe in G, that is a closed polygon with 3 sides, then f is analytic in G. If it is if integral over this f is 0 for every closed triangular path, then f is analytic in G. Let G be a region and f is analytic function with zeros a1, a2, etc. am. If gamma is a closed rectifiable curve which does not pass through any points ak, then 1 by 2 pi I integral over f dash cz by f dash of z dz by f of z is equal to sigma of n gamma of ak. That is, if have a1, a2, etc. are the zeros of this analytic function, if gamma is a rectifiable curve, then 1 by 2 pi I integral over f dash of z by f of z dz is sigma n is from 1 to infinity n of gamma ak. Let fg and gamma be as in the preceding theorem. Let f and g be two open sets and gamma be a closed curve. Then except the points a1, a2, etc. am, the equation satisfies f of z is equal to alpha, then 1 by 2 pi I integral over gamma f dash of z by f of z minus alpha dz is equal to sigma k is from 1 to m n gamma of ak. Using this equation, we can do some examples. Evaluate the integral over gamma 2z by z square plus z plus 1 dz, where gamma is the circle mod z is equal to 2. So we have f of z is equal to z square. If we take f of z is z square plus z plus 1. If a1, a2, etc. are the possible zeros of f over the closed curve gamma, then gamma does not pass through any of these 3 points, then we can say that integral over gamma f dash of z by f of z dz is summation of k is from 1 to m n gamma into ak, n gamma ak. If f of z is z square plus z plus 1, its roots are alpha 1, a1 is minus 1 plus root 3i by 2 and minus 1 minus root 3i by 2. So both the zeros are lies inside the circle mod z is equal to 2. And by the parameterization gamma as 2e raised to 2 pi it, t is from 0 to 1. Since the given parameterization of the circle revolves each of the point in the position orientations. Okay, then we have both lies inside mod z is equal to 2. With a1 is equal to minus 1 plus root 3 I by 2, a2 is equal to minus 1 minus root 3 I by 2. So this gamma wind up both it will round once. So we have n gamma a1 is 1 and n gamma a2 is 1. So by applying this equation, we will get integral over gamma f dash of z by f of z dz is equal to 2 pi I into 1 plus 1, 2, that is 4 pi I. Here is another example. Evaluate integral over gamma 2z by z square plus z plus 1 dz, where gamma is the circle mod z is equal to 2 with the parameterization gamma is equal to gamma is from 0, 1 to c as gamma is 2e raised to 4 pi it. So you can see that here n is equal to 2. That is, gamma revolves each of the point twice in counterclockwise direction.